Hello, myself Shivang Bharti. My project was on lightweight software-defined networking for DebriNet-3. Polar satellite launch vehicles are third-generation launch vehicles of India, which have several stages. One of the stage 4, act as a debris after deployment of satellites in the orbit. So many such PSLV stage 4 can form a network of debris for inter-satellite communication and forming a network economically, which we will call DebriNet. So we have designed a DebriNet version 3 with upgraded version of software and hardware architecture. In a traditional satellite network, we face several challenges such as integration of satellite and terrestrial network. Since it has dynamic routing algorithm, it lacks global view, it has energy constraints and configuration updates too. To handle the problems faced, a lightweight software-defined network architecture is introduced based on software-defined network principle, which is to decouple control and data plane to make network centrally controlled and highly programmable. One of the first standard software-defined network is OpenFlow, but we cannot use OpenFlow in DebriNet because it works on wired medium. It requires higher bandwidth, and due to energy constraint, we have designed a new version, a lightweight version of OpenFlow, which is lightweight software-defined network with all the basic properties working in wireless medium. In our system architecture, we have three components: onboard unit, ground station, and end user. From end user is a common user which will be sending data information to the DebriNet. One of the onboard unit, which is residing in PSLV stage 4, will receive the data, and through the inter-debris network it will transfer the data to ground station. And in ground station we have controller which is there to centrally manage the whole network. Our onboard unit can reside in PSLV as shown in the figure. The onboard unit will have several responsibilities such as receiving data and control information and sending data information. It also has to maintain the storage buffer efficiently and process the data information. In our onboard unit, we have implemented an event handler to handle important events such as beacon reception and buffer overflow management. In our onboard unit, we have also implemented a SQL-based lightweight database management system, which is SQLite, to store and maintain the received data. As in a hardware, our prototype for onboard unit in DebriNet-3 is realized using the components such as Raspberry Pi Zero as a computing module, LoRa as a transceiver module, and different ICs such as real-time clock and watchdog timer ICs. The developed hardware for onboard unit can be seen in the picture. For this developed prototype, a hardware flight test is performed in a weather balloon platform conducted by Department of Earth and Space Science of IST. After the flight test, the payload's computing module, transceiver module, was able to sustain harsh environment, as the balloon was able to went up to 30 km from Pondmudi Observatory, where the temperature was very low and the pressure was very high. Emulation is performed using 4 developed prototypes for a duration of 12 hours. We have considered 2 cases, one with 9 nodes which is having 2 onboard units, 3 end user devices, and 4 ground stations. Another case 2 with 15 nodes which is having 4 onboard units, 6 end user devices, and 5 ground station. We have shown the emulation setup, and corresponding to case 1 we have shown a 3D map of nodes for 2 onboard units which will be deployed in PSLV debris, which are shown in the map, and for end user devices and ground station the places considered are also shown in the picture. As a performance, we have obtained an end-to-end delay, packet delivery ratio, buffering parameters, flow table based parameter for both the cases. As we have implemented SQLite, the new database in our onboard units, which is used to monitor the buffer occupancy and for checking buffer overflow condition. The newly implemented strategy for handling buffer overflow in event handler is also tested and was able to handle a buffer overflow situation successfully. After the emulation results, we were able to conclude that in case 2 with 15 nodes, which shows less end-to-end delay, more packet delivery ratio, lesser buffering time compared to case with 9 nodes, which can be seen in the below table. In one of the performance parameter, end-to-end delay for both the cases, case 1 and case 2, is shown, which shows the end-to-end delay versus number of packets graph, in which for each packet the end-to-end delay is shown. We can see in case 2 the number of packets are comparatively higher received to case 1, and the end-to-end delay, the average and the maximum end-to-end delay for case 2 is lesser compared to case 1. As a conclusion, we can say the hardware was realized for DebriNet-3 using this lightweight software-defined network. We were successfully able to perform a flight test for hardware. We have successfully implemented and tested the design event handler and buffer management strategy. From the emulation, we can conclude that the case with 15 nodes shows better performance compared to the case with 9 nodes, as we have designed a lightweight software which is having a lesser footprint and is lightweight compared to an OpenFlow based software, and the emulation shows that this lightweight software can be a true lightweight solution for DebriNet-3 using SDN principles. Thank you.